Let's go through the setup for this model. Here we have a corkboard which has been raised at an angle to the table surface, making it into a ramp. Here is where we place our marbles, and I've placed some pins in the board in front of the marbles between the top and the bottom of the ramp. So what does all this represent? The surface of the corkboard represents the inside of a wire. The marbles, which will be rolling down the ramp, represent the charges. You can think of them as individual electrons if you like. The height of the marble represents the potential difference. If you remember from last lesson, we saw that the potential difference is the amount of energy that is given to a unit of charge between 2 points. Here, our model uses the gravitational potential energy store to move the marble from the top to the bottom of the ramp, to represent the energy provided by the battery to move the charge through a piece of wire. We could use our model to change the potential difference. If you want to represent a small potential difference, this would mean giving the marble less energy, which we get from the gravitational potential store. And as you know, the higher something is, the more gravitational potential energy it has. So we would raise our corkboard through a small angle. Likewise, if you wanted to represent a larger potential difference, we could use a larger angle. For today's demonstration, we will be keeping the potential difference the same, so we will not be changing the angle. Next, we have the rate at which the marbles will roll down the ramp, which represents the rate of flow of charge, or as we know from lesson 3, this is more commonly called current. We could take this model a little further without the pins. Looking again at the diagrams below, what would happen to the rate at which the marble rolled down the ramp in the low potential difference diagram? We would get the marble slowly rolling down the ramp, which would represent a slow rate of flow of charge, or a low current. The marble would roll down the ramp much more quickly for the high potential difference ramp, representing a high rate of flow of charge, or a high current. Finally, we get to the pins. The pins have been placed in the path of the marbles to resist the motion of the marble. So the pins represent the resistance in our model. The more pins we have, the more resistance we have. So let's take a look at the physical setup that I'm going to use for this demonstration. If we take a look at the top, this is where I'm going to keep my marbles, held back by a ruler. I'm using a ruler so I can release all the marbles all in one go. On the left-hand side, you can see a low resistance wire represented by fewer pins, and on the right, more pins means higher resistance. See if you can work out which side the marbles travel faster. That was a bit tricky to see, so let's take a look at that again, but this time in slow motion. Remember, the left-hand side is low resistance, the right-hand side is high resistance. In which wire is the current the highest? Hopefully you can see there that the wire on the left-hand side, the low resistance wire, allows for a higher current. So let's try measuring that current. For this, we're going to need to use a stopwatch. And we are going to count every marble as being equal to 1 coulomb of charge. And we're going to count how many marbles passed beyond this line in the first second. And that'll give us how many coulombs per second past that point. This will give us a value in amps for the low resistance and the high resistance wire. Remember, there are 6 marbles on each side. Let's pause it at 1 second. On the left, 5 coulombs have passed that line in 1 second, that's 5 amps. On the right, 3 coulombs have passed in 1 second, that is 3 amps.